First of all, what happened?
And the question will be, is the Cavendish axiom of string theory a good curvature? Again, using jargon from another community. Now, I will probably have to skip point 4 because of lack of time. And in any case, I want to use these transparencies for another talk next week, so I put everything. But this time I will. Okay, so the brief reminder, and I want to mention that a physics report on this has just come out by Gasperi and myself at the homepage, and there is an older physics report by the British team. Now, let me remind you the basic idea of this string cosmology is that in order to solve the problem posed by the standard optic band, it is very good to have more time and accelerated evolution. Okay? If you see where the homogeneous problems of standard cosmology come from, they come from two sources. Okay? The fact that there was a beginning of time is one problem. The fact that the expansion is decelerated. Obviously, if you have a phase which goes a singularity instead of away from the singularity, you gain on both accounts. First of all, you have all this time for this extra evolution, and second, going towards the singularity means that the curvature is increasing, the phase shrinks, and you have the possibility of escape going outside of the singularity. Now, when you look at this in the Einstein frame of the string theory, it inevitably means that the collapse phase followed hopefully through a non-singular bounce by an expanding phase. And at that point you can use the powerful Hopkins-Penrose results to argue that this phenomenon is extremely generic if you start with some initial conditions. I want to see a few transparencies telling you about how generic that could be. Let me refer to this possible picture that we developed with Ivona Moore and Alessandro Bonanno. One possibility is to view space-time most of the time and almost everywhere as in a chaotic perturbative state. If you look at the solutions of string theory, weak coupling and weak curvature, they consist of a superposition of matrix waves. Now, in this messy state, I don't think we can even talk about a definite error. But under conditions, and these are the conditions that ensure gravitational collapse, a surface may form now or then, here or there, and it will imply in classical general relativity the onset of gravitational collapse and the formation of a black hole and of a singularity therein. Now, you know that the geometry inside the horizon is typically of a cosmological type, possessed with coordinated timeline, and starts to possess a clear arrow of time towards the singularity. So my belief is that in this chaotic approach to string cosmology, you start with very generic but perturbative initial conditions, and then locally a collapse occurs, and inside the collapse region an arrow of time gets defined, and the Big Bang is produced at the would-be singularity of classical general relativity. Now, you can try to work out how long this collapse has to last in order to produce a big, smooth universe like the one we live in. And some simple calculations show that it has to be bigger than 1 Fermi, the collapsing region. And this has been taken by the cosmological establishment as a big fine-tuning problem for string cosmology. Why? Because one fair being small, but it's much bigger than the other. Okay. So the question is it really a problem for initial conditions? And I think to me the answer is no, but in order to convince people, we tried actually to address this question in simplified cases. For instance, with the Moore spherical collapse, I will not tell you about the results there. Then there has been work by Einstein, Hooks, and Vasquez-Monto on plane wave collisions. You know that when you have homogeneous plane wave collisions, you always form singularities as the two wavefronts collide. At the end of their collision, you form Big Bang-like singularity, which in fact behaves precisely like a Kastner. But of course, these are very special, and therefore, in order to have a better understanding of this finding, we try to go away from exact plane or spherical symmetry to consider the collision of finite shock waves. So the idea of this work is to determine whether a closed-up surface is genetically formed and then estimate the mass, the size of the black hole, study the geometry close to the singularity. Now, until recently, there have been not many solid results as to whether you form holes in the collision of finite waves. Okay? There have been conjectures by you long ago, but not really strong results. But recently, a new method developed by Earthly and Readings allowed my student and myself to find some criteria for the formation of closed-up surfaces when you collide two beams, two massless beams, a generic number of dimensions, a generic impact parameter, and a generic low axis profile, still unfortunately impulsive, namely the waves themselves are very thin. Okay? And I'll give you just a simple example of what happened in the center collision of two identical homogeneous beams. As you like, these were for the PowerPoint show. So show this mainly because I'm proud of it. So what happens is these are the two waves which have a finite transverse dimension RT. They collide, and indeed it turns out that the transverse size of these waves is bigger than twice the focal distance. It's given in terms of the surface density of the waves by this formula. Then you can show and you can explicitly construct a closed-up surface, which is red here, mine, and it ensures that under this condition you form a singularity theorem. Now, this focal distance is quite interesting. You may know that plane waves focalize and what happens in this particular case in which the radius is twice the focal distance is that some of the lasers are deflected by 90 degrees and the ultraviolet and the focus, and well, under these conditions the closed-up surface is formed. So, and I will conclude here on this point, which is not really the main point of the talk, is that it looks to me that the occurrence of gravitational collapse is genetic. First, second, and this you can even guess priori, collapse criteria only involve scales. For instance, you can see immediately there only the beam for the focal distance, or the there is no reference to a string length or a time length. The problem is is completely stable dark. So what we expect out of these chaotic initial conditions is a difference of collapse scales and not just small or big collapses. And we can always use for our universe the tail of this distribution. One fair case. Okay, I go back now to let me go back to transparency number 2. Now I want to simply emphasize in the original Big Bang scenario, the evolution goes from weak to strong coupling, whereas in the chaotic scenario, I'm talking mainly about this version 2, the opposite occurs. Let me show this in a transparency. Big Bang dot. So that's the original one. The evolution phase diagram, which basically has a couple parameter in the string on the vertical axis, and the evolution of the dilaton go increase of the coupling other axis. The starting point is along this line, so it's growing coupling and pressure. And the idea is that string, I forgot to put here, string and loop effect could induce the bounce or the exit as we use it. Okay? Because eventually you want to end up here, because that's the Robertson work by Cosmology we believe to be living in since 11. Now, by contrast, if you look at the diagram for the same diagram for the chaotic, or rather the Big Bang scenario, it basically uses two different things. Of course, you want to end up with Robertson Walker, but the starting point is rather this. You see, I drew here in black this Python constant line. Below this line, the coupling constant is decreasing. Above this line, the coupling constant is increasing. Therefore, this evolution is from strong coupling to weak coupling, whereas this evolution is from weak coupling to strong coupling. This is almost obvious because in this scenario, you start with the two boundary branes far away, which is strong coupling in our field. So, strong coupling in the Big Bang when the extra element goes. Okay, this we have to keep in mind that the avoidance of the singularity. Supposed to occur thanks to corrections or alpha prime or loop corrections. Perhaps there is this difference between the two cases. Anyway, let me. The thing I want to mention about this scenario is that it's capable also of a hot universe, even if we start from a very cold one. Okay? The way entropy is generated, because one of the mysteries of the Big Bang is why there was so much entropy at the beginning, or so little, but anyway, zero. And this is through quantum particle production. Namely, this was to have tiny vectors, and therefore rapid tiny vectors, and therefore a lot of particle production. The perturbations which are on short wavelengths are best described in terms of active particles, and they contribute to the entropy. The large-scale perturbations, which are outside the radius, they can be best described as classical perturbations of metric, series, and so I will not go farther into point 3, simply the fact that scenario generated off Big Bang, not just. But the point of that's the question of large-scale structure, okay? Long wavelength perturbations. Now, string, as you know, has many massless fields, and all of them can participate in structure perturbations. Let me give you some examples. Well, the gravitational set, gravitational waves are produced in this. They come with a so-called tilt or spectral index, which gives the distribution of energy with gravitational waves as a function of frequency. The conventional notation, sorry, are that nt equals 0 is a flat spectrum, r equals the long spectrum. So nt equals 0 means it grows like a third power of frequency. And this result is very robust, sensitive to what we the evolution of the extra dimension in the extra six-dimensional. Such a blue spectrum, as we call it, is good for detection by antennas because it has quite some power at short scales when the detectors work. It's relevant for large-scale structure of CMB and so on. When you look instead at the dilaton couples to the metric. So it's when we talk about scalar, adiabatic scalar perturbations, essentially about the and we found a index ns equals 4, which actually means the same as nt equals 3. It's just a historical question of conventions. So it's also very blue and very small. Now, of course, because according to equilotic claims, this is not, for instance, they claim to get an S equals 1. Now, I don't want to debate, especially here, that you get the blue spectrum. I will not use the equilotic way to cope with large-scale anisotropies. Now, so my opinion, this is irrelevant for CMB. It's also hard to detect because unlike the gravitational waves, we have bounds on the coupling of the scalar component constraints, and therefore when you fold those in, you find the possibility to detect a gravitational waves in there is kind of even worse for gravitational waves. Photons is a very interesting topic because one peculiarity of spin cosmology, as we have seen, is that the dilaton is time dependent. Now the Newton square, and this is something which is not true in standard cosmological scenarios of the dilaton, and therefore you get also perturbations of the electromagnetic fields, short scales, and on large scales, and this gives rise to the cosmic magnetic field. The problem is very complicated though, because electromagnetic evolution is very complicated, so it has not worked out any detail. And one has to also mention that the spectrum light for these two characters, it depends on the evolution of the internal dimensions, and the details how you embed one into the and now let's come to the main dish with the dual of the billion field for dimensions. Now the nice news here, first discovered by the group at Sussex is that the spectrum can be red or even flat. It has, and here I emphasize, it has a fixed normalization. The normalization of this perturbation is given. In this formula, H star is some maximum scale, Hubble scale, or curvature scale that you reach before you bounce. Okay? So I'll roughly call it M straight. Okay? Actually, use H star. I think of it as something like a spin mass. Omega star is the same thing redshifted from the bounds till today. So it's this factor A star over A0. If you have no other inflation after the bounds, it can be estimated at about 10 to the 11 curves. And sigma times is just the canonical axiom. Now, the spectral index, and this is what can vary between 0.53 and 2. I mean, 0.53 plus 4 minus 2 squared to 2. And it's sensitive to what the extra dimensions do. So, for instance, if the 9-dimensional, I'm talking about space, not space time, the 9-dimensional evolved in a symmetric way of duality, then this index is precisely 1. It's really the nice value. So that's not there. Now, however, Kaplan-Meier axiom is isothermal perturbation. It's not the usual what usual inflation does. Entropy perturbation. They are perturbation in a very particular component of the cosmic field, and they don't contribute directly to the curvature of space. Why? I think the simplest way to explain that is that the fluctuations of sigma appear quadratically in the effective axiom. There is no bilinear term which couples the fluctuation of the axiom to the fluctuation of the magnitude, unlike what happens for the dilaton. That's why the dilaton gives adiabatic perturbation, curvature perturbations, whereas the axiom doesn't. And at some point, people doing the less duality transformation, turning on an axiom vector, you could cure this. But what happens is what to do with your S-duality transformation is the wrong object which gets affected. And the guy who couples perturbation always has the glue state. So we see that, and actually, I mean, 2 years ago I was concluding my thinking that there was a problem that might resort to some secondary inflation. Now, the point is that the isotropic perturbations do feed back on the curvature to second order, type perturbations, but they give the wrong structure of the acoustic peaks that you heard have been observed by Budenham, Maxima, and by now quite a few other and other experiments. So this was done in some work by the company. And just to give you an idea, the peak is L equal around 200, and the prediction here was L of 300. Really low. So my collaborators didn't give up at the point. However, there is a follow-up, and this is that we can hope to convert isothermal perturbations into adiabatic ones through a new idea, well, which is not which has been called by Light and Wants the curvature. Anyway, so far I did the computation of the axial perturbations, the assumption is mass, there's no potential. Now we know that with the chain-width symmetry with the axial mass, instantly effects as non-particular effects. Now, if so, a V of sigma is generated and sigma, the expectation value, the homogeneous value of sigma, is not initially at the minimum of this potential, then actually, and you can more or less see, this potential will use now a coupling of the perturbation of sigma and the perturbation of the mesh. Because this is G. So they are couplings, right? They are mixed terms. And one can go on and compute how efficient is the transfer, if you want, of perturbations from the axis into the mesh, into the curve. And okay, this was an idea of Silvia Mollera, but then many people resurrected it in the in cosmology and also outside cosmology. It can be used also for normal equations to, I think, the low scale of still getting. Now, you need two things. You need, in order for this to work, you need a phase axial dominance, namely this massive axial should dominate because it will behave the same dog as a thresholdless and therefore it redshifts as speed compared to radiation. So at some point it will dominate, but it also has to be before the procedure, and for this to happen. Now we computed in a paper with the way these things go, and we found that partly analytically, partly by numerical calculation, this conversion factor. You see that this is the vertical potential, what is very important, delta P over T, and in this factor, it turns out to be of the order of, well, when you square it, order of 0.1, and sorry, last. But we started late, you realize that. We didn't start at 5. Okay. So, we also get just to impress you, to get a formula with all the factors. And I say the factors which is most uncertain, for which we need to know more precisely about how the bounds occurs, is the relation between this H star, which here is additional to a fundamental scale of parameter of string field. Anyway, the formula, and therefore, once you put all the factors in, you can look at the range of parameters which can be consistent with the data. This parameter n, with n scale of CMB, has to be between 0.95 and 1.25. And this, as you see, determines the ratio. It depends completely and only on the ratio of this cutoff over the Planck scale. And notice that, for instance, well, I didn't have time to explain this delta. It's another parameter that you put in. Suppose delta is 0, so it's like easy. Then you get a scaling variance spectrum consistent with the normal calculated data if this H star is of the order of 10 to the minus 3 and Planck, namely is quite close to the ground efficiency. So, the conclusion, we love it. Okay, I think it took many years, as you know, for the original idea of proof to find a consistent framework, become predictive paradigms. Now, the much younger Spectral framework looked like a poor competitor, both because of fine-tuning allegations and also technological drawbacks. But I hope to have convinced you that on both accounts, both on the fine-tuning issue and on the more phenomenological issues, things seem to be going quite in the right direction. So, in my opinion, it's a very encouraging development, which should provide further motivation to this kind of audience, the string community, to address fundamentals. Okay? Because we think now the stakes are really high. So, for instance, we have to address questions like visualize and talk about discussing, consistency or inconsistency of internal acceleration, fate of the Big Bang and other singularities. Now, if these problems will not be solved by then, you are all invited to a Santa Barbara ITP workshop on the subject, which will take place a year and something from now. These are the organizers, and I guess there is already the homepage, webpage where further information can be found. Thank you. I'm sorry.
Questions? Questions?
Thank you, Gabriele.